There we go. All right, so another DDoS research talk here. So I'm a security researcher with Arbor Networks. If you don't know Arbor, we do DDoS mitigation products and services. And this is the story of a strange DDoS attack that we saw that we were unable to explain and how we did some research to get to the bottom of it. If you've already jumped to the conclusion that it has to do with IoT and SSDP, you'd be correct. That looks strange, but so before we begin, you kind of have to understand how SSDP works. So if you're on a laptop and you want to print a document, well, nobody has a parallel port on their laptop anymore. Nobody wants to type the IP address of a printer into their settings because it's 2018. You just expect printers to appear. So this protocol called SSDP, which stands for the Simple Service Discovery Protocol, will help your laptop discover services that are on your local network. So when you go to print, your laptop will send a request for any devices on your local network that have services to announce themselves. And the way it does this is it sends a UDP packet to a well-known multicast address on UDP port 1900. And pretty much every single service discovery packet looks the exact same. It's got this M search. It kind of looks like HTTP, even though it's running over UDP, but it's really not. So anyway, so your laptop sends this discovery packet to the network, and for every for every service that's available on your network, you'll get a response back, and the response will be from the response will be a unicast packet that is from the IP address of the printer or whatever, and the source port will be 1900. And it will reply to your ephemeral port that you sent the search on. And the response is also UDP, and it looks like HTTP, even though it's really not. So the important fields here are, it shows you a location, which is an actual TCP-based URL that if your laptop will go to, it will list all of these services available. It'll be able to interact with it via SOAP, which is not really germane to this conversation. But one of the fields that I didn't include here, but is kind of weird, is that a lot of these implementations will respond with a user agent, which is coming from the response, not from the client, which is kind of weird, but we'll get into what that is in a minute. So a long time ago, years ago, attackers figured out that they can abuse this protocol. So most SSDP implementations will send one packet that contains a description of each unique service available. So if I send one mSearch packet to a printer, and the printer is, it's a fax machine, it's a scanner, it's a printer, I might get any number of response packets. So in other words, sending one packet results in, anywhere up to a dozen response packets. So attackers figured this out very quickly. If they send an mSearch packet to a unicast address, which could be anywhere on the internet, it can elicit, a dozen response packets. And if they set the source IP address to a IP address of a target they would like to launch a denial of service attack on, they could flood their network essentially with response packets. So that's all very straightforward. Mitigating this attack is also pretty straightforward. At several of your network points, you could just filter out UDP packets that have a source port of 1900, and the attack will be mitigated. So that's all fine and dandy, but one attack we noticed was very strange. So this attack started off as a normal SSDP attack, and the victim just filtered source port 1900 UDP at their network boundaries, and then something strange happened. The attack shifted, and they were still getting flooded with SSDP response packets, but they were from ephemeral source ports and destination ports. So if you look on the right there in Wireshark, you can see that those are pretty much just random ports. And that bypasses any sort of port filtering you might have in place, because it's essentially two random source or random port UDP packets flooding your network. And they're clearly SSDP, they're SSDP responses. And of course, to mitigate this requires a little more lower level inspection. You have to look at the contents of the packet to see that it's a UDP packet that has an HTTP response. Then you drop those packets. but we weren't really sure why this was happening. It was really strange. So as is very fashionable these days, we decided to figure this out by scanning the entire internet. So as a proxy for a random port, a random ephemeral source port, we used a static port of 1901. It doesn't have to be 1901. We just used one static port. And the reason we did that was so that we could record the responses that come back to that port. And literally all we did was just send the msearch packet to every address on the internet, recorded the responses, and tried to figure out what was happening here. So of all of our responses, I divided them into two different buckets, the behaving and the misbehaving. So the behaving group, I would get responses that were destined for that had a source port of 1900. And the misbehaving responses were of a source port something other than 1900. And what was immediately striking is that there are way more misbehaving SSDP implementations on the internet than there are behaving. So that's really strange. So what's going on here? So in addition, I recorded the first service response from every single response that I got. Oh, I forgot to mention too, we got like, I think it was 5 million responses. So basically 0.14% of the internet has a eliciting SSDP implementation on it, which I thought was interesting. But anyway, remember how I said in the response packets, sometimes the user agent is set, which is strange because it's a HTTP response and not a request. But one thing that really stood out was that in the behaving responses, there was overwhelmingly no user agent installed. On the misbehaving, it was overwhelmingly this red Sonic user agent in the packet. So doing some creative Googling, we found this open source project called libupnp, which is reused by everybody pretty much, or 56% of the internet apparently. It actually hard codes this red Sonic user agent into it. And we're going to release a paper that talks a little more in depth about some of the other aspects that we found, because it's not just the red Sonic user agent that pointed us to libupnp, but that was by far our most damning piece of evidence. So this open source library is used in all sorts of CPE IoT devices. It's used in DVRs, it's used in webcams, it's used in lots of different stuff. So 2 minutes left. So just to summarize, the library code that exists in these IoT devices, sometimes these devices are really hard to update. So even if we did fix this, which I'm not even sure it'd be considered a bug, it's just some sort of strange behavior. But even if we did fix it, this code is going to live on these devices for a long time, just given their large install base. But the more important point, I think, is that the attackers are aware of this behavior, and they will shift their tactics. If one attack isn't working, they will focus their attack on this more random source port. And of course, to block these attacks requires much deeper packet inspection. So it will require you to look at all UDP packets to see if they have an HTTP response that looks something like SSDP. And if you do that and drop those packets, it will mitigate the attack. And that's pretty much it. We have 1 minute left if there's any questions.
Job Snyders, NTT Communications. It's not per se a question, but a follow-up to your recommendation. NTT just rate limits SSDP traffic to 1% of the port's capacity, and this greatly reduces the fallout from those packets. And I would recommend my partners and competitors and customers to just do the same. We should not see SSDP traffic on the global internet. So
exactly, it should be on the local network. And
put it in the trash queue.
Exactly.
Thank you.
Thank you.
All right.
All right, cool.
Thank you, man.